We will continue with our lectures on process control. In the last two lectures, I talked about Laplace transforms, how we could use Laplace transforms in solving differential equation models, also called by us as state space models. And I also introduced this notion or idea of transfer function models for the first time in this course. We saw that a transfer function model is just a function in the Laplace domain that is used to understand how the input affects outputs and so on. In this lecture, I am going to start with a summary of what we have learned till now. The reason for this summary is the following: while we go forward with this control course and we start doing more manipulations with Laplace transforms and differential equations and so on, I do not want all of the material to look too abstract, completely mathematical. I just want to take a break here and then summarize and say, look, all of this started from a physical process, and all of this modeling and the math should serve us in understanding the physical process and in understanding how to control the physical process. Now, this tank example was a very nice example. We saw that you have this basic flow in, flow out and height as the three variables. And then we saw that basically physical model of this should allow us to understand how, when things change, either when f naught changes or fi changes, how height changes and so on. So, the idea of the model itself is to be able to explain what is happening here. So, we basically wrote fundamental conservation equations, constitutive relationships and so on for this, and then we got to a differential equation of this form: tau dh by dt equal to minus h plus some k fi, where fi, if I assume, is the inlet flow rate and that is what is here. And then you also had a relationship between the outlet flow rate f naught and h and so on. Now, the thing to remember is that this, while it has now become a parameter in this equation, this embeds all the physical parameters of this system, like area, and if you are linearizing from a nonlinear equation, then the steady state value of height and so on. And similarly, this k, which is now a parameter in this equation, also represents the same thing. So, an equation of this form and an equation that relates f naught to h together, we said if you want to do this in a general form, we can call this as this state space model, which is x dot equal to ax plus bu and y equal to cx. Again, this a, b and c are basic translations of tau, h, k and so on. So, it is basically constants which come from the first principles modeling that we have done. So, if you really draw a picture like this and then say, how do I understand changes in flow affecting, let us say, changes at the outlet flow rate, your notion is basically there is some time profile that is happening for this, and I want to know what happens at f naught. Okay. Now, this, when we do this mathematical model something like this, then in the time domain, if I put in a block like this here, then I might say there is a u that comes in and a y that goes out. And when I write a block like this, then basically what I am saying is this u is some time function and this y is some time function, and I want to know how y changes when u changes. Okay. So, though I just write u and y, this is u of t and y of t. The reason why I am putting this in block is because this is a block in the real tank block. So, here again there is some input fi and actually some output f naught that we abstract out as a model of the process, and if this is an ordinary differential equation like what we have been using till now, then this model is basically in the time domain. Okay. So, the reason why I am doing this is I just want to emphasize again that this time domain model has constants which reflect reality. They are not some abstract numbers that comes out of somewhere. Now, in Laplace transform, what we do is the following. So, we say, look, if I have this Laplace transform, then I can convert this u to u of s. Okay. Then this goes into this transfer function model, which is somehow this ODE converted into the transfer function model, and then I can get my y of s here. Now, notice the way these blocks work. So, when I want to get y of t from u of t in this block, then basically it is actually some integral equation that I have to solve to get y of t as a function of u of t. So, it is not a simple u of t is something time y of t is something like u of t, it is actually some function which you have to compute, given u of t you will compute y of t. This function is something that we showed in the last lecture. Whereas, when you look at this block the interpretation is, if I have a transfer function model here g of s, this block is in the Laplace domain, and if I want to get my output variable y of s, it is very straightforward, it is simply multiplying g of s times u of s, and this g of s again has parameters which come from this ODE, and those parameters come from the physical system. So, g of s is also representing the physical system, albeit in Laplace domain, whereas this ODE model is representing the physical system in the time domain. So, let us not lose sight of this fact that while we keep talking about transfer function models and we will just talk about ns by ds, numerator by denominator and so on, those are not just mathematical constructs, they are actually representations of physical systems. So, that is something that I would like the young students watching this to keep in mind. Now, this is single input single output. Now, if you have more inputs, because of linearity assumption, things are quite simple. For example, if there are 2 inputs which affect the output, then there will be 2 transfer function models. We will see this in more detail later, but I just want to explain this here so that you understand how these blocks work. So, y of s, if there are 2 inputs, could be something like g1s u1s plus g2s u2s. So, this basically says the effect of the inputs u1 and u2 are additive because underlying model is linear, and the effect of u1s is moderated by some transfer function g1s, and the effect of u2s is moderated by some transfer function g2s. Now, this g1s and g2s, the parameters in those would reflect the actual physical parameters of the system that is being modeled. Now, it might be that there are not 2 inputs, but there is 1 input and 1 disturbance, in which case we will write y of s is g of s us. So, the standard notation is I will do a subscript here g p for process, and then I could write g d of s d of s. This subscript is to talk about the disturbance that affects the system. So, the total output that I see from the physical system is a combination of the effect of the manipulated variable, things that I am changing affect y, and also an effect due to the disturbance variables which are changing by themselves, and the effect of the disturbance variables are moderated by gd of s. And we can always write this as additions because we are assuming that the underlying system is linear, and because it is linear and we can use the linear superposition principle, we are able to write these equations. So, ultimately when we go and then write an equation like this d of s has a physical d of t which is actually a disturbance variable changing in time, and this u of s has a physical u of t which is actually some manipulated variable changing with time. So, in the tank example, if I put in a control valve here and then manipulate the inlet flow rate, then Fi will become this ut, the physical variable that is changing, and if I do not control anything here based on the pressure difference and the resistance here, F naught will change, but I will have no control over it. So, it will become a disturbance variable. Instead, if I were to put in a control valve here and then I manipulate F naught, then F naught will become u of t, and Fi, which is uncontrolled and any amount of flow can come in, I really do not have a control over that, will become d of t. So, this u of s and d of s are actually Laplace transform of real physical variables, something that I want you to keep in mind. So, in general we could write the output as g of s u of s. If you had a disturbance, you could write it as g d of s d of s, or in a generalized form we can write the output as some transfer function multiplied by some input that makes a difference as far as output is concerned. So, for example, if this is a disturbance variable, we will call it d of s, which basically says what is the effect of the disturbance on the output. If I of s is u of s, then we are asking about what is the effect of the input on the output. If I of s is something else which we will see later. Then we have something called the closed loop transfer function, which we will talk about later. But I wanted to introduce this notion that the output is basically a product of a transfer function and some input, and if there are multiple inputs that affect the output, then because of linear superposition we can simply add these effects. So, if we write an equation like this where y of s is g p of s u of s, where we are trying to see the effect of the manipulated variable directly on the output, then this transfer function is typically called as the open loop transfer function. Okay. So, this is the open loop transfer function. Now, if we write the effect of a disturbance variable on y of s, here I have some terminology which we will come back to later. This is a moderating function which is a closed loop transfer function on how the disturbance affects output. We have not yet talked about closed loop transfer function, so we will come back to that later, but for now you might simply assume this as some transfer function which moderates the effect of the disturbance on the output. There is another input which we have not talked about, which is the set point. So, y set point of s, if that is the input, then the effect of that on y we call that as a closed loop transfer function, right, and these two we will see once we define what a controller is and how you handle controllers and so on. Nonetheless, the reason why I want to introduce these ideas here is that anytime you do an analysis of transfer function, ultimately all you are doing is something like this, g of s times I of s. Now, this g of s will be derived based on what system and what structure that you are using. However, if you are simply looking at how you would analyze control systems with transfer function models, once you learn how to analyze control systems with transfer function models which are generic g of s, I of s, then you know how to address any type of system. So, that is the reason why I introduced these concepts here. And we also talked about a general form for g of s. We said g of s is some numerator divided by a denominator, and the numerator polynomial is of order r, let us say, and the denominator polynomial is of order n. Then as long as r is less than or equal to n, we call gs as a proper transfer function. That means the numerator order is less or equal to this order, we call it a proper transfer function, and if it is strictly less than the order of the denominator, the numerator order, then we call it as a strictly proper transfer function. So, these are two definitions which are used in control literature. So, now let us say you have this y of s is some g of s, I of s which we have. Now, what we are going to start doing is clearly to get y of t, you need to know g of s, which is something that will come out of the modeling, and you also need to know what I of t is. So, whatever is the variation that happens with this input, then you can convert this to I of s, and then you can get y of s as g of s times I of s, and then once you get y of s, then inverse Laplace transform will give you y of t. So, that is the general flow that we are going to see as far as control is concerned. There are certain interesting things that we would like to compute about y of t. So, the first idea is what is called a final value theorem, where you are saying, okay, if y of s is some g of s times I of s, I want to know what happens as t tends to infinity. That basically means if I let this system run for a long time, will my output value settle? If it will settle, at what value will it settle, and so on. So, mathematically this question you pose as limit t tending to infinity y of t. Now, this is already proved. So, what this theorem says is, if you want to know limit t tending to infinity y of t, you can get this value by equivalently looking at limit s tending to 0 s y of s, right. What is the importance of this theorem? Typically, if you wanted to get this, you will have to first convert y of s to y of t and then put this into this and then say limit t tends to infinity. But this is a simpler approach. If you want to get the final value, you can directly use the variable in Laplace domain itself and then get the limit. So, that is the reason why this theorem is interesting. So, for example, if we have let us say g of s, and we will talk about this quite a bit later, is of the form k tau s plus 1. So, this is what is called as the first order transfer function, okay. And then let us say I give an input which is a step. So, g of s is this, u of s for a step input we have already seen that the Laplace transform is 1 over s. Now I want to know, once I step my input, what will be the final value of my output. So the steps to follow is, first we will get y of s, which is g of s times u of s, and then we will use the final value theorem, which says limit t tends to infinity y of t is limit s tending to 0 s times y of s. Y of s is g of s times u of s. Now this s and s will get cancelled, and when you substitute s equal to 0 here, you will get this value k. So if my transfer function is of this form, then the final value that y will take whenever I perturb the system as a step input is k, which is what is given here. Equivalently, you can ask the flip question, if I want to know what will be the initial value of y of t, and this is not really useful for y of t itself, but we are going to use this later, where we can find the initial value of dy by dt. So basically that will give me what is the initial slope that y is going to take, or initial rate at which y is going to change. So if I want limit t tends to infinity y of t, then I can calculate that as limit s tends to infinity s y of s, right. Now you can see how they are kind of symmetric, t tends to infinity, s tends to 0, t tends to 0, s tends to infinity, and s y of s is the same. Okay. Now as I said before, this might not be useful for y of t itself, but we could ask questions like limit t tending to 0, what is dy by dt. So this will be limit s tending to infinity, s we will say Laplace of dy by dt. Okay, we already know that Laplace of dy by dt is s y of s minus y of 0, and if you assume that y of 0 is 0, then this would be simply limit s tends to infinity s squared y of s. Okay. So you could apply these theorems for not only y of t, you can apply it for dy by dt, d squared y by dt, or any other function that you choose. So when we start analyzing these transfer functions, and then we start using these transfer functions, these are important concepts that will come in handy as we go through in control. These two particular theorems are going to be quite important, because I am going to use this later when we describe offset and so on, and this we will look at in much more detail when we talk about zeros and poles later in terms of performance limiting factors in control. Okay, so that basically tells you that there are theorems which you can use to compute some basic numbers without actually going through the whole inversion process. However, in general what we would like to do is we would like to get y of s, g of s, I of s, and then from this we want to get a value for y of t. Now typically each one of this, let us say g of s in a standard form will be some numerator polynomial by a denominator polynomial, and I of s will also be some numerator polynomial by denominator polynomial. So ultimately whether it is g of s, I of s, or y of s, we have to really look at a numerator polynomial by a denominator polynomial, because I could say this is again n of s by d of s, where n of s is n1s times n2s and d of s is d1s times d2s. So ultimately it does not matter what you are trying to invert, whether you are trying to invert g of s, you are trying to invert I of s, you are trying to invert y of s, you are going to try and find the inverse Laplace transform of a ratio of polynomials, numerator polynomial by denominator polynomial. Now whenever we talk about polynomials, we know that we can write them in root resolve form. If we keep the first coefficient as unity, then we can actually write the expansion in this form. So we talked about an order of a system, and then we said the degree of the denominator polynomial is the order of the system. So if it is an nth order system, then the denominator polynomial is going to be nth order, and we know from our algebra that nth order polynomial will have n roots. So we have d of s written as s minus p1, s minus p2, s minus pn. This is something that we had seen before, and when I write an equation like this for the denominator, this p1, p2 all the way up to pn are called the poles of the transfer function, or the poles of the system itself. Okay. So the roots of the denominator polynomial are the poles. Similarly, the numerator polynomial can also be written in a root resolved form, which is s minus z1, s minus z2 all the way up to s minus zk, if k is the order of the polynomial, numerator polynomial. In this case, the roots of this z1, z2, z3 all the way up to zk are called as the zeros of the system or the zeros of the transfer function. So, if you set the numerator polynomial to 0 and then compute the roots, then those roots are called the zeros of the transfer function, and if you set the denominator polynomial to 0 and calculate the roots, those roots are called as the poles of the transfer function. So, as I mentioned before, generically whether it is g of t, y of t, I of t, we have to do an inversion and we have to do an inversion of ns by ds, right. So, let me assume that I am trying to get a g of t from g of s, right. This could be y of t from y of s, I of t from I of s, does not matter. So, this is going to be as a numerator divided by denominator. So, the Laplace inverse of this I can write as n of s divided by this. Now, I have made it little more sophisticated because I am going to talk about a general solution to this. So, this looks little busy with mathematics, but it is not that difficult. It is a quite a simple straightforward algebra. So, you have to just follow the notation little carefully. One of the problems with when we talked about roots of the polynomial and so on, in the previous lectures, to simplify matters, I had assumed all the roots are distinct or different, but supposing you have, let us say, a fifth order polynomial, it could be that all the roots are the same, they are repeated 5 times. So, for example, if you take a polynomial of the form x minus 2 to the power 5, if you set it equal to 0, x equal to 2 is the only root, but that is repeated 5 times. Okay. So, what we then say is, to generalize this, every root in the denominator polynomial, which is a pole, let us say p1 to pr, each of these poles can be repeated many times. If they are not repeated at all, then I will have n poles. But let us say if one pole repeats and nothing else repeats, I will have n minus 1 poles and so on. So, we generalize this by saying, let us assume a pole p1 is repeated k1 times, pole p2 is repeated k2 times and so on. If that is the case, then the denominator polynomial can be written as s minus p1 power k1 times s minus p2 power k2 all the way up to s minus pr power kr. The important thing to notice here is there cannot be more than n roots. So, k1 plus k2 all the way up to kr has to be n. So, for example, if I have a fourth order polynomial and I have only 2 poles, okay, either each pole has to be repeated twice, or one pole is repeated thrice and the other one is single, or this is repeated not repeated, the other pole is repeated thrice and so on. So, these are the possibilities if you have 2 poles. But notice always that 2 poles, there are 2 numbers, 2 plus 2 is 4, 3 plus 1 is 4, 1 plus 3 is 4. So, there are always these number of repeats have to add up to n. Okay. So, now if we want to invert this, what we are going to do is the following. We are going to repeatedly apply this rule. You can go and look up the table for this rule and understand this well. So, what we are going to say is, in general, if we take Laplace inverse of 1 by s minus pi to the power r, the inverse is t to the power r minus 1 e power pit by r minus 1 factorial. Okay. So, this is already computed. We are going to keep using this again and again, there is nothing new here. Once you understand what this is, then it is going to be straightforward application of this to find the inverse Laplace transform. So, how do we use this? I am going to give you a very simple example. Let us assume that I have, let us say, some g of s, which is a numerator polynomial n of s divided by, let us say, a 6th order denominator polynomial, and this 6th order polynomial has 2 roots p1 and p2. p1 is repeated 4 times, p2 is repeated 2 times. So, 4 plus 2 is 6. So, that is the reason why I call it 6th order. So, when I write this like this, now when I do a partial fraction expansion, the simple rule is you will get as many terms for a root or a pole as its repeats. So, for example, p1 is repeated 4 times. So, I am going to get 4 terms for p1. So, the first term will have in its denominator s minus p1, the second term will have s minus p1 squared, the third term will have s minus p1 cube, and the fourth term will have s minus p1 to the power 4. And P2 is repeated twice. So, the first term will have S minus P2 and the second term will have S minus P2 whole squared. So, it is very simple pattern that keeps following. So, if it is repeated 5 times I will have one more and so on. And whenever I have something like this, then as I told you before in one of my previous lectures, that the information from the numerator is all hidden in this constant C11, C12, C13, C14, C21, C22. So, the notation we have followed here is P1 is repeated 4 times. So, 4 terms are there have to be 4 constants. So, C11 is the first constant where the power is 1, C12 is the second constant where the power is 2 and so on. And similarly, this is for the second pole, C21 is for the second pole with power 1 and C22 is for the second pole with power 2. Notice that I have not said how we are going to compute these C11, C12, C13, C14, C21, C22 yet. However, I can guarantee that if I have this numerator by denominator where the denominator is of this form, I can always write this in this partial fraction form, and these constants will exist such that when I reduce all of this I will get back my numerator n of s by d of s. So, let us follow the logic that we have been using till now. So, I said we can write any analysis of transfer function as y of s is g of s times I of s. G of s is a numerator by denominator polynomial, I of s is a numerator by denominator polynomial, and y of s is also a numerator by denominator polynomial. So, as long as we learn the technique, so how to invert numerator by denominator polynomial, find the Laplace inverse of this numerator by denominator polynomial into time domain, then we can solve all kinds of problems. We do not have to really worry about how we will do the Laplace inversion again. The only question will be how do I get the transfer function, how do I get the I of s and so on. So, what I am trying to show here is a generic solution for ns by ds, and I said that minute we have a polynomial we have n roots, but it is not that all roots need to be distinct. So, we have multiple roots repeating, and we have come to a state where the inversion of this n of s over d of s is simply finding the Laplace inverse of this. Again, just to reiterate, I have not shown you how to compute the C11, C12, C13 and so on, which we will see in the next lecture. Nonetheless, I can guarantee that if the denominator is of this form and the numerator order is less than the denominator order, I can always get a partial fraction of this form with the correct C11s, C12 and so on. Okay. So, now when I do the Laplace inverse of this, I have a Laplace inverse of the whole sum, and again appealing to the notion of linearity, Laplace inverse of the sum will be Laplace inverse of an individual term and add them all up. So, this will be Laplace inverse of the first term plus Laplace inverse of the second term and so on. And if you notice carefully, an interesting thing happens right now. If you notice each of these terms, okay, to find a Laplace inverse of all of these terms you have to only use this rule here. So, if I take the first term, so this is Laplace inverse of 1 by s minus pi power r is 1. Okay. So, if I put r is 1 here, t power 1 minus 1 is 0, e power p1 t divided by 0 factorial, which is 1. So, the Laplace inverse of this is simply C11 e power p1 t by 0 factorial. Let me take just another term which is a little away from here, and you can work out the other terms. So, let us say I take this term here and I go here, I see that r is 4. So, this should be t power 4 minus 1 t cube e power p1 t divided by 4 minus 1 3 factorial. So, if you see the Laplace inverse of this, it is C1 4, which is a constant which is yet to be determined. I have to tell you how to determine that. Nonetheless, if you had determined that already, this is going to be t cube e power p1 t divided by 3 factorial. And similarly, you will get every one of these terms, because every one of these terms looks like this here. And it is not anything specific to this example that these terms look like this. Any time you have the transfer function in a numerator by denominator form, I can always guarantee that I can put this in this partial fraction form, and the minute I put it in the partial fraction form, it is very trivial to write the inverse Laplace transform, and the inverse Laplace transform keeps using this again and again. It repeatedly applies this to get the solution. So, ultimately when I want to get the inverse Laplace of ns over ds, which could be ys, gs or is, then I get this here. Now, notice that p1 is the root. So, we already know what the value of the root is based on the denominator polynomial. p2 is also root, we already know what the value is based on the denominator polynomial, and t is again a time function here, t squared, t cube and so on. The only thing that I have not yet shown you is how to get these constants out of for this partial fraction to work, which we will see in the next lecture. But nonetheless, the key point that I want to make here is, irrespective of whatever is your polynomial, this technique will always work. Okay. So, the question of inverting these transfer functions becomes understanding only one formula right here right now, so that we can do this quite easily. So, I will stop here as far as this lecture is concerned, and then we will go on to looking at how to get these constants and how to generalize this further in future lectures. Thank you.